Morning everyone. So today is going to be the last lecture delivered by me. So tomorrow you're going to have Tracy talking about how this theory is helpful for showing the certain Markov chains or fast mixing. So Tracy will tell you about that. So today my goal is to connect matroids and this completely log-concave or Lorentzian polynomial. So I'll be using CLC and Lorentzian interchangeably. Okay. So recall definition and some facts that we learned from last time. We said that for today, all of today, we're going to assume that a polynomial is homogeneous and non-negative coefficients. Homogeneous. Okay, so a polynomial, such a polynomial is called completely log-concave if for any sequence of vectors in non-negative directions, this repeated directional derivative is log-concave on the positive orthant. Right. So we also saw that these things work now. So equivalently, to check the log-concavity, you can look at the Hessian. So this is the matrix of a partial derivative with respect to xi and xj of right, all these things that you're trying to compute the log-concavity of. So this Hessian is negative semi-definite for all x in the positive orthant. And we also saw that this is that. We also saw that Hessian of the log G can be written as 1/g squared. G, which is a scalar, times Hessian of G, which is a matrix, minus column vector gradient of G times this transpose, which is row vector. And this thing, being negative semi-definite, is equivalent to this Hessian of this polynomial itself having at most one positive eigenvalue. So that's just what we talked about today. But let's think about how to show whether a given polynomial is Lorentzian, right? So this is huge amount of things that you need to check. You need to check that for all sequences of direction, that is infinitely many, right? And then you need to check the log-concave on the entire positive orthant, that is another infinitely many, right? That is extremely very many, okay? So it was shown in the Brandin and Hall paper that this CLC is equivalent to SLC, strongly log-concave, meaning that instead of looking at all the directions, it's enough to look at the coordinate directions. Right? So one consequence of, so we're trying to reduce this amount of check to a finite computation. So that's the goal here. Right? So maybe the goal is that, the goal is to reduce it to finite computation. So from Brandin, they show that maybe it was known earlier, I'm not super sure. So strongly log-concave is equal to completely log-concave. In other words, that means that it's enough to check the VIs in coordinate directions. Yeah. So all we need to worry about is say sigma. I'm going to denote sigma to the alpha. By that I mean if alpha is a tuple of non-negative integers, right? By this notation, I'm going to let sigma 1, right, alpha 1 times, right? So sigma 1 is partial derivative with respect to the first variable and so on. And sigma n alpha n times. Okay. Right, so it's enough to look at these finitely many derivative with respect to the variables instead of looking at all the directions, right? So we have reduced that down to reduce this part down to finite, right? We still have to deal with this log-concave on all the positive orthant, right? So there's a special case one. This is a finite check. This is for my polynomial or the partial derivative. Polynomial is degree 2, quadratic, right? When it is quadratic, then this Hessian is a matrix with constant entry. It's just numbers in it, right? And then you can check whether something is negative semi-definite, right? Otherwise, this matrix, if this polynomial is high degree 3 or more, right? That means that this matrix has entries in the polynomials, and you just show that, right? For all choices of positive number, it is negative semi-definite, right? So it's infinitely many conditions. But for degree 2, it is a finite condition, right? So you may wish, right? You may wish that it is enough to check log-concavity. For the partial derivative, which are quadratic. That would be very nice. That would be a finite monogen. Okay, because Hessians or quadratics are matrix with real entries. You can do the computation. But it turns out that this is not true. Right? So this particular wish is not going to come true. But right, is it enough? I guess this is the question mark. Is it enough? Right. So unfortunately, here is a very simple example. It is not enough. For example, if you look at x cubed plus y cubed, f is equal to x cubed plus y cubed. And if you look at quadratic partial derivatives, so one is 3x squared, it's just 3x squared. And with respect to 2, it is 3y squared, right? So these are stable, therefore Lorentzian, but you can show, I won't do the computation, but this one is not Lorentzian. Okay, so it's not enough to check the quadratic partial derivative. Some extra condition is needed. So we need an extra condition. So I'll show you 2 types of extra conditions that you can use. Maybe I'll show you one is coming from like sort of matroidal, like support being matroidal, and another one is, well, is saying something about the polynomials are not too disconnected. So right here, this is on different collection of variables, or maybe another way to see this is if you look at the exponent vectors right here, this is 3, 0, and 0, 3, right? So if I look at the exponent of these monomials that appear, look at it. There are some points missing along the line, so that is part of the issue. So we want to kind of capture that. So I'll give you 2 theorems. One theorem is I'll state, but I will not prove. And then I will try to prove a second one. So I'll give you 2 set of extra conditions that you can pick and choose. Okay, so one is this is a theorem by Anari, Liu, Oves, Garan, and Vincent. maybe I think the third one. Right, so under the same condition, F is homogeneous with non-negative coefficients. So F is completely log-concave. If and only if all the partial derivative with respect to the variables are indecomposable. I will define this in a moment. Decomposable. For all alpha, this is by this bars, I mean the sum of the coordinates. Okay. Less than or equal to d minus 3, where d is the degree of F. So that means if you look at the partial derivatives, which are degree 3 or more, has to satisfy something called indecomposable condition. I'll write down in a moment. And that is enough to check. Under this condition, is enough to check a log-concavity. Write down what indecomposable means. So to do that, if you have a polynomial f, I'm going to associate to it a graph whose vertices are partial derivatives, which are the variables such that the partial derivative is not identically 0. And then the edges are pairs of vertices I and j, such that the partial I, partial j is not identically 0. And when I say polynomial is indecomposable, means that this graph is connected. Okay. So it is a finite check for each of these, there could be very many because you have to look at, right, all the partial derivative down to degree 3. And yeah, let's look at some example. So for example, if f is x1, x2 plus x2, x3, right? So with respect to each of the variables, partial derivative is not identically 0. So my nodes, my vertices are 1, 2, and 3. And then for the edges, you're looking for pairs of variables that appear together. Right? So right here, x1, x2 appear together. x2, x3 appear together, but x1, x3 do not appear together. So this is indecomposable. But if you look at if they're on kind of disjoint set of variable, like x1, x2 plus x3, x4, then only 1 and 2 appear together, and 3 and 4 appear together, like that. So the graph is disconnected, so it is not indecomposable. So this theorem, that's not very easy to. So it is proven in the paper but this reduced the problem of checking Lorentzianness to a finite computation. And I want to give you a different combinatorial conditions, I think, which is interesting in its own right. It's not just for computation, but it is important in the study of Lorentzian polynomials. So I want to spend some time discussing the Newton polycopes and supports of the Lorentzian polynomials. Now, in a different direction. Let's see. So in a different direction, we will be looking at supports of the polynomial. Over there, we're also looking at the supports. Support meaning the monomials that appear in my polynomial. Right? So when I say that if I have my polynomial, let me set some notation. So say alpha, right, C alpha x to the alpha. Right, so my notation is the x to the alpha means, I don't know if I exit, so x1 to the alpha 9, xn to the alpha. So if I have a polynomial like this, the support. So we're not thinking about, you might have seen support analysis where support of a function is when the function is non-zero. So right here, we're not talking about function as a polynomial. We're talking about the monomial support. So this is all the alpha such that this alphas are in C to the n, such that C alpha is not zero. Okay, so this is all the monomials that attach to a non-zero coefficient. So, and then we have Newton polytope. I'm going to denote N of F, which is the convex Hall of the support. It's the smallest convex set containing a support. So if you have 2 points in my support, I have to connect with the line, right? And I keep connecting all the points. So let me do an actual example of an actual Lorentzian polynomial. So yeah, so I just made up some random Lorentzian polynomials so that I could draw pictures. This is degree 3 in 3 variables. Right, so to get to the support lies, so it lies in Z3, but it lies on a hyperplane of coordinate sum equal to 3, which is a triangle. So it lies inside a triangle. Right, so this is the same triangle you saw in Chris's talk on the first day. Right, so with the vertices 3, 0, 0, 0, 3, 0, and 0, 0, 3, but the 0, 0, 3 is not in the support because we don't have a z cube term, right? As you can see, but we have right. So along this line, this is my x cube. This is x cube, and this one is y cube. And along this line, these correspond to monomials in x and y only. Right. So this is x squared y, and this is xy squared. And along here, this is z cube, but z cube is not in my support. So in the middle, it is xyz. Right, this is 0, 2, 1, y squared z. This is yz squared. Along this line, it is x and z only. So this is 2, 0, 1, x squared z, and 1, 0, 2, xy squared. Okay, so support consists of all the points that I drew except this z cube. So support consists of these 9 points. Okay. And then the convex Hall is I connect, right, all the dots to each other and also have to like fill in the inside. So convex Hall, this is my Newton polytope. So here's a definition that comes from discrete convexity. So definition, but this is not the official definition, but it's an equivalent characterization of M convexity. We say that a subset, let's say S in C to the N is called M convex. M stands for matrix. That will be clear in a moment why it is connected to matrix. So it's called M convex if you look at the convex Hall of S, this is a polytope. It is a higher, possibly higher dimensional, right? Polyhedral object like this. So higher dimensional generalization of polygons, things like cubes and octahedron and things like that. So this polytope has edges in directions, in the difference of coordinate directions. So I'm following synthetic of denoting 1i minus j, right, or ei minus ej in these directions. And that it contains no holes, meaning the S is equal to all the lattice points in the convex hole. Yeah. So the second condition says no holes. So right here in this one, I have this red convex hole and I cannot have points missing either in the interior or on the boundary. I cannot have any point missing, right? So you can see in this example that this polytope is M-convex, right? Because if you look at the edge direction, right, this is in the, this direction is right, let's see, -1, 0, 0, 1 direction. So that means it is in the 1, 1, 3, minus 1, 1, E3 minus E1 direction. And similarly, I have all these difference of coordinate directions. Okay, so this is M-convex.
What? Why is that -1, 0, 1?
Because the point up there is 0, 0, 3 minus the point down here is 1, 0, 3, 0, 0. So it is right, so -3, 0, 3. I'm just rescaling it.
Well, there it's 0, 3. I'm sorry.
Oh, I'm sorry. Sorry. I pointed in the wrong direction. Okay. Thank you. Yeah. Yeah. It's right here. Okay, thanks. Okay, so -1, 0, 3, 0, 1. Okay. Thanks. Yeah, so the first one is about the Newton polytope. And then the second condition is that there can be no holes in the support. So the support has to be as dense as possible given the Newton polytope.
Is this related to the exchange axiom?
Yeah, it's related to the exchange axiom. Maybe I will note that here's a fact or theorem of Galfond, Gorasky, Matheson, and Saganova from the 80s, maybe 87, is that if my S is a subset of a 0, 1 to the n, right? So if my integer vectors are only allowed 0 and 1, and 0, 1 to the n, I am going to identify them with subsets of 1 through n. Right? Because 1 indicates, which factors are in my subsets. Right, so you can think of this as a collection of subsets. Then I say that this set is, it follows from this theorem that S is M-convex, if and only if it is the set of bases of a matrix. Bases of a matrix in the way that we defined on the first day. Yeah, so M-convexity is a polyhedral characterization of being a matrix. The whole condition doesn't matter in this case because this thing in a cube that is, the cube is small enough that there is no space for holes to appear. So the whole condition is automatically satisfied. You only need to check the edge directions. Yeah, so this is a generalization of a being matrix to a bigger collection. You can also call these a polymatrix. So like Chris said on the first day, polymatrix. I don't know about multimatrix. Okay, I think these are polymatrix. Yeah, so you can imagine that maybe you can think of you taking some elements multiple times. Maybe these are multimatrix. I don't know. Kind of like multisets. Right. Okay. Now let me give you the theorem of Bredin and Hook. Is that right? Remember, our goal is we want this finite check for the Lorentzianness. So they said the F is Lorentzian and only if its support is M convex. And you still have to check your quadratic partial derivatives. So this quadratic partial derivatives are log-concave. For all alpha, which are size t minus 2, so these are quadratic concave. Always on the positive. So I want to go through a proof of one direction, the forward direction, okay? So this second condition follow from the definition. So just I want to prove that if F is Lorentzian, then the support is M convex. Okay, so there are two things to prove. There are the things that no holes, and there is the thing about the edge directions of the Newton polytope, right? So to pick out the edges of the Newton polytope, what is the corresponding algebraic operations that you do to the polytope that will pick out an edge? So some of you have already seen it. This is the process of taking initial forms. Okay. So let me do it in this example. I might have to erase this. So if I take a back vector, now our goal is to try to prove that Lorentzian implies support is convex. Convex. And then let's do the edge directions. So for that, let me define some notation. So for W and Rn, and if you have a polynomial F, we can define the initial form in W of F is defined to be, let's see, again, F is the sum of C alpha, no, sorry, alpha in the support of C alpha x to the alpha, right? And alpha is the sum over, you sum over not all alpha, but you only pick out the alpha that maximizes the dot product with the W. Okay, I'm going to write it as argmax, right? Of all the alpha such that W, the dot product is maximum. Argmax. Okay, alpha of W dot alpha, okay, over the support. Alpha in the support. Okay, so you pick them out of C alpha x C alpha. So let's do it in the example. If I want to pick out this edge over here, okay, this blue edge, then if I will maximize, for example, if I take W to be 0, 1, 1, okay, if I take W to be 0, 1, 1, then the dot product for these guys is going to be 3, right? Dot top product for this one is going to be 2 and 1 and 0. So maximum is going to be along the blue ones. Is that okay? Yeah, so in this example, hint 0, 1, 1 of F is just going to be these 3 terms corresponding to the ones without axis, right? This one, and that one. So it's going to be 4y³ plus 9y squared z plus 5y squared. Yeah, so these operations of taking initial form allow you to pick out faces, right? Polynomials whose Newton polytopes are faces of my original polytope. So I'll write that down. Then the Newton polytope of the initial form is equal to a face. In our case, we're only interested in the edge, so it's going to be the edge of the Newton polytope in that direction. Okay. So next I want to claim that if F is Lorentzian, then the initial form is also Lorentzian. So this was on the exercise sheet yesterday. But it's the last one, so maybe people have not gotten into it, so I'll go through that. Right, so one way to think about this is that, say, to get to this initial form, what you can do is, right, so if you want to do, there's the claim, if you want to take initial W of F, then what you can do is you take F and you replace variable X with an extra variable, T to the W1, X1, up to T to the Wn, Xn. Right, and then you have a bunch of T's, and then we are picking out, right, the one that win, the one that are going to show up in the initial forms are the one attached to the maximal W, maximal T powers. So the T is finding the maximal thing for you. Okay, so what you're going to do is you're going to divide with the maximal. So you're going to take this, and then you're going to take T to that maximal dot product. So that means that the initial form doesn't have any more T, but the other ones come with T's in the denominator. And then if you let the limit as T goes to infinity, then they all disappear. Okay, so let's do an example. And to get to this initial form, I take my original form and I look at my F of, I don't touch the X because, you know, this is, I have W0 is 0, so I have T to the 0, which is just 1. Now I have T to the 1 times Y and T to the 1 times Z. Right? If I plug in to my big polynomial, right, my X cubed is not affected, right? My 410 X squared Y, it picks up a T. And then 17XY squared picks up a T squared, right? And so on. So if I collect it according to the T, so this is going to end up with T cubed times 4x cubed plus the one doesn't have an X. Comes with the T cubed. And then I have T squared times something plus T times something. And then without T, just X. So if I do that substitution, now I divide by T cubed, because to get rid of this, right? So now I divide by T cubed, divide this thing by T cubed, and then this thing goes away, and then now T is in the denominator. As I let the limit of T goes to infinity, I'm left with just the initial form. Right? So if I click, so the limit as T goes to infinity, I'm left with the initial form that I want. Okay, and then let's see why it preserves the Lorentzianness, because all we have done right here is we're scaling the variable, right? If you scale the variable, that doesn't change the concavity, okay, right? So then this, yeah, preserve this like log-concaveness of everything. And then the limit thing, and then also, you know, this is dividing, this is for a single fixed T, right? Scaling keeps the Lorentzianness, and then dividing also keeps the Lorentzianness, you're just scaling. And then the limit comes from the fact that the space of Lorentzian polynomial is closed. Okay, so in the case of Lorentzian, it's by definition. So there's a claim F is Lorentzian, the initial form is also Lorentzian. So if we're interested in the edge direction using the operations of taking initial form, we have picked up a single edge to look at. Okay? Now we're looking at a single edge. Now we're reduced to the case of a single edge. So if you now the edge is living somewhere. Okay. Now so there might be, right now we haven't proven that there are no holes. So there may be some holes, right? So the support on the edge looks something like this. Okay? And then I want to claim that by taking partial derivative, you can reduce it to a binomial. So what does taking partial derivative do to a Newton polytope? Yeah. So may shrink it, right? So taking partial derivative sort of like shift it down in the coordinate direction, right? Taking partial derivative with respect to x1, shift it down in the e1 direction and so on, right? So I'm bringing this edge, and then, when it hit the wall, when it hit the coordinate plane, you might lose a point, right, into the wall, right? So then, by taking partial derivative, you can sort of like chop up vertices, like shave off the vertices from the end. Okay, by taking this and bringing it down in the some coordinate direction. By taking partial derivatives, I can chop them up until I'm down to just 2 points. Yeah, is that okay? I'm a little bit hand wavy, but right. So I take the partial derivatives sort of repeatedly, right? So we get a binomial whose binomial, right, in the same direction, whose Newton polytope is the same direction at the edge. Whose polytope is in the same direction. By taking partial derivative doesn't change the direction, it shifts them down, and then it sort of chop off things at the end. So binomials, what do binomials look like? Something like a times x to the alpha plus b times x to the beta, right? And also taking further partial derivatives, say if both alpha and beta contain x1, and then you can take a partial with respect to x1. Okay, and so you can reduce the degree. By taking partial derivative, you can assume that alpha and beta, this x to the alpha and x to the beta, the monomial, they're on disjoint collection of variables. Yeah, does it make sense? They both contain, x1, you take partial with respect to x1, right? Until one of them don't have any more x1, right? You keep doing that, right? So again, take more partial derivative to assume that x to the alpha, x to the beta are on disjoint collection of variables. And now they are in disjoint collection of variables, and then I could take the first collection of variable and substitute y into it, and take the second collection of variable and substitute z into it. All right, because this variable substitution also preserves our Lorentzianness or log-concavity. It is kind of like slicing with, x equal xj kind of hyperplane, and like log-concavity, like inside there. Okay, so variable substitution preserve Lorentzianness, so you can like sub, right? So they are in disjoint collection of variable, you sub y and z for those two collections. So to get some polynomial, after you take the variable, maybe it's no longer C and B, A and B, but maybe some other coefficients, you might have changed it, right? So it will look like, y to the something, right? Y to the something, I don't know, y to the k plus s times c to the k. You reduce to this kind of thing, right? And then now, this is still Lorentzian, right? Because variable substitution is Lorentzian. But if you look at things like this, if the degree is 2 or more, and if you look at the Hessian, right? then it's going to have, so this is just 2 by 2, Hessian just 2 by 2, right? Then it is going to have something positive here, something positive here, and 0 here, right? This is the Hessian. It's going to 2 by 2 and looks like this. This has 2 positive eigenvalues, so it cannot be Lorentzian. So this is if k is bigger than or equal to 2. Okay. So that means that k has to be at most 1. Yeah. It has to be at most 1. So that means that after I undid all my operations right here, what it means is that the only binomials are Lorentzian, right? So only binomials are Lorentzian have the form something times xi plus something times xj, right? Some degree 1 step times some monomial. Yeah. And this one is in the edge is in direction ei minus ej. Yeah. So we have done the first part of the proof. Okay, so the Newton polytope has edges in directions ei minus ej. And I should mention that those polytopes are also called generalized permutohedra. So if you have same permutohedra, they are obtained by taking permutohedra and moving the facets parallelly in and out without changing the edge direction, right? So it's the first part. Maybe for the second part, I'm just going to talk it out because we don't have too much time. There's one more thing I want to do. So for the second part, so this implies, maybe I should say that this implies that the edges of Newton polytope of any Lorentzian polynomials are parallel to ei minus ej's. Okay, so this is the edge part. For the no hole part, right? For the second part, to show that things don't have a hole. This actually shows that along the edges, I don't have a hole. Okay, because all the edges are in direction ei minus ej, and then these things cannot be further apart. Okay, so from here, this also follows that there are no holes along the edges. But what if you have a hole somewhere inside my polytope, right? Somewhere deep inside the polytope. So what you can do is you can do an induction on the dimension of the face containing the hole, right? So by the base case is the edges cannot have any holes. So it follows from here. So the idea is the one that when you hold this inside, now you assume that if the hole is on the interior of the face, then you can again take the initial ideal thing and pass it to the face, and that reduces the dimension of the Newton polytope. Maybe I should write it down. So proof of no holes. So it is going to be induction on dimension. Okay, so dimension 1 follows from the discussion above over there. So follows from and then if the whole dimension of Newton polytope. So if there is a hole on a face on the boundary, right? Take the initial form with respect to appropriate direction to pick up the face, right? Take initial form and pass to the face. That will reduce the dimension. Pass to the face. And in other words, by inductive hypothesis, it cannot be, right? Cut to the face and then apply induction by inductive hypothesis. Now you are reduced to the case one, there is a hole in the interior. So it exists a hole in the interior of the Newton polytope. Let's say I want to show that this thing is not a hole. What you can do is you can take directional derivative to expose the hole, right? In this case, you take this, and if I take directional derivative and I just like shift it this way, this thing got shaved away. I'm left with the smaller Newton polytope. And then my hole got exposed. It becomes on the boundary, and I can apply the induction again. Okay? There is a little bit something to be worried about. Like, for example, if I have this is not a generalized Fermi-Hydra. If I have my Newton polytope like this, and the directions are not in the EI minus EJ directions, right? And then, like, say I want to show that this is not a hole, right? And if I just take a directional derivative, right? And then if I sort of chop off this vertex, then my Newton polytope is just this edge, and my hole is sort of not exposed. It's not on the boundary, it just like disappear altogether. Okay, so that kind of thing cannot happen because of this special edge direction business. Okay, so yeah, you have to use that. But yeah, so the idea is that if the hole is in the interior, then take directional derivatives to expose the hole. Yeah. So this is the idea of how you can prove that Lorentzian polynomials have M convex support. So that's why the study of Lorentzian polynomials is intricately linked to the matroids. So even if you're not interested in counting independent set or whatever, you cannot get away with matroid if you're doing the Lorentzian polynomials. So in the last 10 minutes, I want to get back to these Mason's conjectures and the basis generating polynomials of matrix. So now that we have the tools to prove some polynomials are Lorentzian. Here's the term. I think this was first proven by Anari, Oves-Garan, and Vincent, I believe. So if M is any matrix, I'm sure it's also in the rendering. So M is any matrix, then on ground set N with basis B, and then let Fm be the basis generating function. This is generating polynomial x to the b. So the notation as before is x to the b is the product of I and b. So this polynomial is completely log-concave. And moreover, yeah, I'll just do the independent set version as well. So moreover, if I is the script I is collection of independent sets of the matrix. You want to look at independent set generating function, right? X to the I, but the trouble is that this is not homogeneous because independent sets can have different, right? Different sizes. So you just homogenize. So to the at minus size of I. So now this is a homogeneous polynomial of degree n. So this is living in, right, in one higher one more number of variables. So this is also completely log-concave. I think I might just have enough time to go through a proof of the first one. Second one is similar, but the computation is a little bit more involved. So for the proof of the first one, you have to check using the theorem. I don't know if it's still there or not. I might have erased this, right? So for the proof for the first one, so the first thing that you have to check is that the support of Fm is M convex. Well, support of Fm, right? So these are all the 0, 1 vectors, whose are the corresponding to the bases, and this is true by this result I mentioned, Gelfand, Gorowski, McPherson, and Zaganova. Now we have to check the log-concavity of the partial derivatives, right? So let's think about what happens if you take a partial derivative of this basis generating polynomial with respect to x1. What happens to the matrix? Okay, this was on the first day exercise sheet. Anyone remember? Yeah. Yes, it's either deletion or contraction, right? Okay. So right here you kill all the, so maybe think about a tree, right? You pick an edge, right? And then you take the partial derivative with respect to that edge. That means that you ignore all, all the trees that do not contain the edge, right? And then you throw it away. Okay, so is that deletion or contraction? Yeah, that is contraction. Right? So partial derivative with respect to, so to check log concavity. Right. So you look at partial with respect to some set, because these are all like, they don't have higher degree, these polynomials, right? All the there are no degree 2s or 3 or all the degrees are 0 or 1. So you only care about like collection of variables to take the partial derivative with. So for us, in 0, 1 to the n, the partial derivative with respect to this s variable of Fn is f of the contraction. And then we're only interested in the ones where this contraction is degree 2. So contraction, and then you assume that suppose that means that this matrix has rank 2. Because we only need to check with quadratic. Check quadratic. Okay, rank 2 matrices are very easy to understand. So there's not too much that can happen in rank 2. So if you're thinking about, say, a vector matrix, right? If you're thinking about the vector matrix, then, on a vector space and a 2-dimensional vector space, right? Any 2 vectors form a basis as long as they're not parallel, right? So the only thing that you have to worry about is whether they are parallel or not, right? So the elements come in parallel classes, and that's the only interesting thing that is happening for the rank 2 matrix. All right, so for the rank 2 matrix, so for rank 2, it breaks up rank 2 matrix. Right, so this collection breaks up into parallel classes. And then using that, let's try to write down the Hessian of this matrix. So Hessian of this construction. So what does it look like? Okay, so I'm going to, the matrix also may have loops. Loops means that these are the elements that do not appear in any basis, right? That means that the corresponding columns are all going to be 0 columns, 0 rows or 0 column that do not affect my negative semi-definiteness. So I can ignore them, right? So we can ignore the loops. Okay. So ignore the loops, right? Suppose they never even existed. And then the rest break it into parallel classes. Maybe some are big and some are small, right? So it comes into this block structure, right? And then within each parallel class, so elements that are not parallel, any pairs of non-parallel elements, they form a basis. So that means that the non-parallel ones form a basis. And then within each parallel glosses, right, any two of them do not form a base. So my SCN looks something like this. Okay. Okay, and then we want to show that this one has, at most one positive eigenvalue. Right, so we can, let's rewrite this, right? So you can take this and you can say, right, you can take a big matrix of O1 minus a block matrix of ones down the blocks. Yeah. So this O1 matrix is rank 1, but this is column 1 times the row 1, right? Okay, and then yeah, so the blocks are here, the blocks are parallel glosses. Okay, so this matrix is positive semi-definite because you can see that each little block is this is a column with some 1 times its transpose. Right? And then this block is the columns of like this short ones times the transpose, and now this one is a rank 3, right? So this thing is positive semi-definite with the negative is negative semi-definite. So anyway, this one is positive semi-definite. And then this one is rank 1. And then from Cauchy interlacing or things that we talked about last time, this whole thing can have at most 1 positive eigenvalue, right? The intuition is the positive eigenvalue is only coming from here, right? Because of this negative sign, these ones have non-positive eigenvalues, right? So from the results from last time, this one it has 1 positive eigenvalue. All right, so this is the idea of a proof for the first statement. For the second one is a little more complicated because now you have to take the derivative with respect to y's as well, right? Taking derivative with respect to x is exactly the same. With respect to y, then it's a little more complicated. You have to look at analyze the special case one. There is a y square and a y, right? Then kind of similar calculation show what you needed. All right, so this is the end of everything I want to talk about. Thank you. Questions? Like then we don't have a moderators. Yes. Yeah.
Could you maybe explain again why this analysis in the top board gives that we have no holes?
Oh, okay. Why we have no holes? Yeah. So, okay. So right here, by taking a partial derivative, right? If I have a hole, so I can zoom in, right? Taking partial, I can just zoom in around the hole to just the 2 endpoints of the hole, right? And then I can still have this entire the same analysis or the same argument to get to this this conclusion. And then this binomial here has no hole.
Then you don't plug top of this binomial.
That's right, because this binomial has just length 1, right? Because this xi and xj has length 1, so it has no hole. So, okay, so because if you just zoom into the 2 endpoints, of the hole, right, it's going to look like that. So it also implies that there cannot be no hole. Like between 2 consecutive points along your edge, right? And between any 2 consecutive points, it looks like this, and there is no space to have a hole in here.
You mentioned the 2 theorems. One is this one here, and on the
Yes.
right hand side we have the 2 conditions. And the other one is like Lorentzian if and only if like the second condition is the same, but the first condition is the support of F is M convex.
Yeah.
So how does like support of F M convex condition, does it relate to the?
To the indecomposable, I believe that, you know, in general, I think they don't imply one another. Yeah. So this is only in this special case of checking Lorentzian-ness that you can use one condition on the other condition. As like a purely combinatorial conditions,
M convex should imply ND convex.
yeah, that's right. Okay, yeah. So thank you, Tracy. Yeah, M convex is stronger. M convex implies this, but this one certainly does not imply M convex. Yeah. You can do something like, yeah, you know, like x1, x2 plus x2, x3 plus x3, x4. This will be indecomposable, but it will not be M convex. Yeah, so okay. So Tracy said M convex implies indecomposable.
Why do you homogenize up the number of elements rather than the ring?
Yeah, that's a good question. So I think it doesn't matter. So I think if I could have done it to the rank, and then this one is just the extra R's lying around.
It doesn't work if you homogenize up to rank.
No, you mean like it's not?
It's not Lorentzian.
Ah, okay, thank you. Yeah. Yeah, I guess that also makes sense. Okay, yeah, I should mention that, yeah. So this one implies the Mason conjectures, right? So this one implies the strong Mason. Yeah, so in the strong Mason, you will remember that in the denominator, we have the n choose case happening. And then, yeah, so Tracy is saying like, yeah, if we can do it to the rank, we would have like R choose case in the denominators, and I think that doesn't work.
In the triangle example you gave us, if the middle one is a hole, if we don't have 1 on 1, what does taking is convex hole mean? Taking the convex hole of the boundary.
Oh, yeah, taking convex hull will fill it up anyway.
Oh.
Yeah, so convex, like, you know, by definition, convex hulls don't have holes. When I say no hole, I mean like the support, right? And the support is as large as possible, right? Suppose contain all the integer points in the nuclear orbital.
Just to confirm, we're taking the convex hole in Rn, right?
Yes, convex hull and Rn. Yeah, so, but in these cases, because we're talking about homogeneous polynomial, they live in a lower dimensional plane, but yeah, convex hull. Well, maybe one very last statement. So because some of you, you know something about tropical geometry, so I'm not gonna maybe even connect a little bit to melody, although this is a different type of tropical geometry, right? So you can define all these like Lorentzian over a real field with valuations. And then you can look at, for a polynomial, you can look at valuations of the coefficients, right? So taking a valuation is a form of tropicalization. So one statement that you can derive from using like the same ideas I discussed is that if you look at Lorentzian polynomial with fixed support with valuation, then the collection of valuation gives you M convex functions on the support. So like the tropicalization of Lorentzian polynomials give you M convex functions. Yeah, so this is one connection to tropical geometry that we haven't explored. Okay, I think, no moderator, so I think I need to end this. Let's go have coffee.